Welcome to The Debate. For decades, the holy grail of neuroscience has been, well, reading human thought.
Right. Interfacing directly with the mind.
Exactly. Whether that's to cure paralysis, treat depression, or eventually augment our own cognition. But our current method for doing this is, it's essentially stabbing the brain with a silicone needle and wondering why the brain fights back.
Yeah, it's a brute force approach.
It really is. So what if, instead, we could read thoughts by simply placing a synthetic, self-powering, quantum optical web on the very surface of the brain? Today, we are examining an independent proposal by researcher Zachary David Enfield for an organic quantum interface.
Which is a theoretical framework aiming to entirely replace traditional penetrating brain-computer interfaces, or BCIs.
Right. He proposes an ambient, amyloid aromatic biological scaffold instead. So the core question we are exploring today is whether the future of neuroprosthetics actually requires this kind of fundamental quantum biological paradigm shift to bypass the brain's immune response.
Or, on the flip side, if this proposed interface relies on biophysical assumptions that are, just too speculative to actually work in a living human.
Right, and I will be arguing that this proposal represents a rigorous, conceptually necessary evolution, one that finally speaks the brain's native language.
And I'll be taking the position that while this paper offers a devastatingly accurate diagnosis of why current BCIs fail, the proposed cure leaps far beyond what is plausible.
You think it's an overreach?
A massive one. A quantum scaffold operating via excitonic transport in the warm, wet, chaotic environment of human physiology is, it's a brilliant piece of theoretical physics, but it relies on a highly precarious tower of assumptions.
Well, to set the stage, we really have to understand why the current BCI paradigm is doomed by its very first principles. Think about the progressive signal degradation we see in long-term implants.
Like the Utah array?
Exactly. Or even the newer, flexible polymer threads. They slowly stop working over months or years. And historically, the field has treated this as a mechanical failure, right? A materials problem.
We try to make the electrodes softer.
Right, we try to reduce the rigidity of silicon, which has a stiffness of about 200 gigapascals, down to match the incredibly soft 15 kilopascal texture of brain tissue. We use hydrogels, flexible polymers, but that fundamentally misses the point.
Because the degradation of the signal isn't a mechanical failure.
Exactly. It is a biological success. The brain's immune system, specifically the microglia and astrocytes, is detecting a foreign surface chemistry.
It doesn't matter how soft the silicone is.
No, it doesn't. The brain recognizes it as an invader and walls it off with a thick glial scar. It's essentially the brain's way of encapsulating a microscopic splinter. The brain doesn't need a softer electrode. It needs an interface made of its own molecular language.
Which is where Enfield's thesis comes in.
Yes. He proposes using a yeast-derived amyloid scaffold specifically engineered with amino acids like tryptophan and tyrosine to couple directly with the native quantum pathways of the brain. It is a structurally brilliant way to completely bypass the immune response.
Yeah, I absolutely agree with the critique of the current electrode paradigm. We are basically trying to stick a rigid sword into a highly sensitive, gelatinous electrochemical network.
Right.
And then we act surprised when the network attacks the sword. The reality of oxidative stress and reactive microglio encapsulating foreign objects is, it's the great bottleneck of neuroengineering.
Exactly.
But jumping from the failure of silicon to a synthetic quantum optical mesh is a massive overreach. The author is relying on non-contact energy transfer across the boundary of the brain.
Which we'll get into.
Right, and he's expecting a non-mammalian yeast protein to perfectly align its molecular structure with neural dendrites. It completely ignores the messy, noisy reality of a living organism.
Well, let's break down that physical material shift first. Because if we both agree the traditional electrode is biologically untenable, we have to look closely at the structural viability of this replacement.
Sure.
Enfield targets the SUP35 N-terminal domain. It's a specific peptide from yeast. Now you might ask, why put a yeast protein on a human brain?
It does sound counterintuitive.
It does, But the brilliance here is that because it is a yeast translation termination factor, the mammalian brain has no evolved immune program against it.
It bypasses the glial scarring cascade entirely.
Yes! It doesn't trigger the misfolded protein alarms that something like Alzheimer's amyloid beta would. It registers as biologically stealthy. On top of that, it forms a cross-beta sheet spine, giving it immense structural stability.
Which he needs for the engineering side of things.
Right. Think about it this way. Inserting traditional silicon into the brain is like trying to seamlessly splice a modern, delicate fiber optic network using heavy copper wire.
It's clunky.
It isn't just clunky, it misunderstands the fundamental nature of the medium. We need an organic substrate to talk to an organic system.
The copper wire versus fiber optics analogy is striking. I'll give you that. But let's look at the molecular engineering required to make that organic substrate actually function as a fiber optic cable.
Okay, let's look at it.
The paper relies heavily on the precise geometry of that cross-beta sheet spine. In this structure, the strands have a spacing of exactly 4.8 angstroms.
Which is incredibly precise.
For context, an angstrom is 1/10,000,000th of a meter. We are talking about unimaginably tight atom-level spacing. The theory is that if you insert a tryptophan residue at every fourth position in this protein, you get this perfectly spaced face-to-face stacking of their aromatic rings.
Exactly, the pi-pi stacking. It creates a seamless parallel array of conduction pathways. The rings act like a microscopic pathway of stepping stones, allowing quantum energy to hop rapidly down the line.
Yes, in a vacuum, or in a highly controlled laboratory assay. The author cites surface-enhanced Raman scattering studies showing that electrons can delocalize and flow across these structures in lab settings.
Which is proven physics.
Proven in a lab. But we are talking about maintaining a perfect, uninterrupted aromatic highway in a living, breathing, metabolizing brain.
Right.
A fibril trying to self-assemble right on the surface of the brain is going to be bombarded by surrounding proteins, enzymes, and the constant wash of interstitial fluid. If even one stray molecule bumps that 4.8 angstrom alignment, the highway breaks.
You think it's too delicate?
It is theoretically beautiful, but maintaining that pristine geometry inside a living skull strikes me as incredibly fragile.
I hear the skepticism, I do. But the pi-pi stacking interaction isn't just some fragile incidental feature that happens to survive if it's left completely alone.
It's not?
No, it is actually one of the primary thermodynamic driving forces of the fibril assembly itself. The structure structurally wants to form this way.
Oh, I see.
Yeah, replacing those residues with tryptophan actually accelerates the formation of the amyloid. It snaps together like perfectly polarized magnets. But let's follow your line of questioning into the actual mechanism of signal transmission.
Let's do that.
Because if we assume the physical scaffold can be constructed and holds its shape, we have to address the core provocative claim of the paper, that the brain operates via quantum optical computing at the terahertz scale and that this synthetic scaffold can read it.
And this is exactly where the paper departs from classical textbook neuroscience.
It does, but it does so backed by an accumulating density of quantum biology research. We have to look at the microtubule, which is the structural scaffolding inside our brain cells.
Right.
Each tubulin dimer inside that microtubule contains 86 aromatic rings. Now, the classical objection to quantum biology has always been that a warm, wet brain is too thermally noisy to support quantum effects.
Right. The assumption was that quantum states need near absolute zero temperatures to survive.
Exactly. But we now have the established mechanism of phonon-assisted quantum transport. We see this in photosynthesis.
Plants use it.
Yeah, plants actually use the chaotic thermal vibrations of their environment to help bounce quantum energy exactly where it needs to go with near-perfect efficiency. The thermal vibrations of the protein scaffold don't destroy the quantum coherence.
They sustain it.
Yes, they sustain it. The brain is likely using its own ambient heat and vibration to channel energy down these pathways. The scaffold end field is proposing just acts as an extension cord to tap into a quantum process that's already happening.
Hold on, let me stop you there. Let's assume, just for the sake of argument, that the microtubules inside our neurons are indeed exhibiting quantum coherence.
Okay.
The mechanism this paper relies on to transfer that highly sensitive quantum state from the inside of the brain out to the synthetic scaffold is called Foster Resonance Energy Transfer, or FRET.
Yes.
FRET is a non-contact coupling mechanism. It's essentially like wireless charging for molecular energy.
Right. It operates through dipole-dipole coupling without any physical connection. The energy just jumps across the gap.
Exactly. It jumps across a physical gap of 2 to 5 nanometers between the device on the surface and the dendrites of the brain cells beneath. And here is the critical detail that makes this so precarious.
Let's hear it.
FRET efficiency decays at the inverse 6th power of the distance.
It is a steep mathematical drop-off, sure.
It is an exponentially unforgiving drop-off. I mean, if you double the distance between the transmitter and the receiver, the signal doesn't just cut in half, it drops by a factor of 64.
Wow.
Yeah. If that 2 to 5 nanometer distance fluctuates by even a fraction of a nanometer, your signal-to-noise ratio is completely destroyed. Now look at the architecture of the device itself.
You're talking about the energy harvesting.
Yes. To power this system without toxic chemical batteries, Enfield proposes a highly complex energy harvesting system. One of those modalities is a piezoelectric layer.
Right.
Piezoelectric materials generate electricity when they are physically bent or squeezed. This layer is explicitly designed to harness continuous macro-level mechanical deformations, the physical pulsing of blood from the heartbeat, the waves of cerebral spinal fluid, the pressure changes from breathing.
Right. Ambient movement.
But how can you have an architecture that relies on harvesting the gross, physical squishing of the brain on one layer while simultaneously depending on a hypersensitive 2 to 5 nanometer wireless energy jump on another layer?
I see what you're saying.
The sheer physical movement required to power the device would continuously shatter the precise alignment required to operate it.
You're looking at that physical pulsing as a bug that disrupts the system, but the design actually leverages it as a conformal feature.
How so?
Well, you're treating the surface of the brain like a rigid table being shaken by an earthquake, where things would slide around and misalign. But this is a conformal biological interface.
Meaning it bends with the brain?
Exactly. It is a highly flexible web designed to rest seamlessly on the glia limitans, the brain's outermost membrane. It rides the wave of those cardiac pulsations in unison with the underlying tissue, rather than grinding against it.
But still, the nanometer scale.
The 2 to 5 nanometer gap is maintained locally because the scaffold is bound by the exact same fluid dynamics as the dendrites it is reading. They move together, like two ships tied together riding the same ocean swell.
That's a very poetic image.
And frankly, that brings us to how this thing powers itself, which I find to be one of the most brilliant aspects of the proposal.
I will certainly grant that it's an ambitious power system.
Ambitious, but elegant. I mean, we are trying to build an interface that lasts for years, maybe decades, without a surgeon ever having to go back in to replace a battery. So, it uses a trimodal system.
3 power sources.
Right. First, you have a beta-voltaic contribution. They weave tiny amounts of carbon-14 or tritium isotopes directly into the scaffold backbone, providing continuous nanowatt power through natural radioactive beta decay.
Okay.
Second, you have the piezoelectricity we just discussed, generating power from the heartbeat. And third, you have the thermoelectric Seebeck effect.
Harvesting heat.
Exactly. This harvests energy from the temperature gradient. The brain cortex is metabolically hot, running about 2 to 7 degrees Celsius warmer than the scalp.
Right.
The device captures the energy of that heat dissipating outward, like catching the draft between a hot room and a cold window. You have an interface that literally uses the brain's own metabolic heat, its rhythmic pulsing, and its native atomic decay to power its readouts.
Wait, let me make sure I'm picturing this right, and that the audience is picturing this right.
To Ed.
I don't deny the conceptual elegance. As a theoretical exercise on a whiteboard, it's a masterclass in synthesis. But the integrated complexity is staggering.
It has to be complex to work.
But let's look closely at layer 2, the biomineralization layer. Enfield proposes embedding nanodiamonds into this yeast protein scaffold to act as magnetic sensors.
Right.
Then, in layer 4, we are bonding a nanoscale integrated circuit to manage the power and code these delicate quantum signals and transmit them wirelessly outside the skull.
Yes, the processing layer.
Add in the radioactive isotopes, the barium titanate for the piezoelectricity, the nanodiamonds, the silicon circuit. We are risking recreating the exact immune rejection the architecture was designed to avoid.
I disagree.
You've taken this biologically stealthy yeast protein, but you've loaded it up with so much synthetic hardware that it essentially becomes a nanoscale landfill, resting right on the surface of the brain.
A nanoscale landfill, that's quite a term. I understand why listing all those components sounds alarming, but we have to look at how they are spatially arranged.
Okay.
It is not a landfill where everything is mixed together in a pile. It is a meticulously layered composite. The only layer physically touching the brain, layer 1, is purely the SUP35 amylaromatic scaffold.
Right, the stealth layer.
Exactly. The immune system, the microglia, they operate purely through surface chemistry recognition. They are blind to what is behind that surface. They do not have ground-penetrating radar.
They just read the surface.
Yes. If the layer touching the brain presents a hydrophilic, protein-coded language that registers as benign, the subsequent layers of nanodiamonds and circuitry above it are effectively cloaked. The immune system is not triggered because the biochemical trigger simply isn't touching it.
That assumes the composite never degrades over decades, releasing those radioactive isotopes and nanodiamonds into the highly sensitive cortex.
Well, rigorous testing would be required, obviously.
Right. But let's push past the hardware viability for a moment. Let's assume the scaffold self-assembles perfectly. Let's assume the wireless energy transfer survives the respiratory movements. And let's assume it powers itself without triggering an immune response.
Okay. Giving me a lot of credit there, but I'll take it.
We still have to arrive at the ultimate purpose of the device. What are we actually decoding here?
This is where the capability shift becomes truly profound. The proposal specifically targets the dorsolateral and ventromedial prefrontal cortex.
The areas of the brain responsible for high-level executive function.
Right, and working memory. The anatomical reality is that layer V and layer 3 pyramidal neurons, which are deep inside the cortex, have these massive, elaborate dendritic trees.
Okay.
Think of them like towering redwood trees, whose roots are deep in the brain, but whose highest branches extend all the way up to the very surface, right beneath the protective membrane. This means the BCi can access the deep substrate of working memory without ever penetrating the tissue. It just sits on the surface and listens to the highest branches.
Right. It reads the signal right at the boundary.
But more importantly, it changes what we are reading. Current BCIs read the macro-scale action potential, the electrical spike. As Enfield points out, if the quantum optical layer inside the cell is the actual computational engine of the brain, the action potential is just the printout.
The printout?
Yeah, it is the end state of a cognitive process that has already been completed. Think of it this way. Reading the action potential is like standing outside a football stadium and hearing the crowd roar. You know a goal was scored, but you don't know the mechanics of the play. By accessing the quantum transport in the microtubule, we are tapping into the coach's headset. We are decoding the underlying semantic intention. We are reading the decision as it crystallizes, not just the downstream electrical twitch it eventually produces.
And what's the clinical application?
This could allow for closed-loop neurofeedback that corrects pathological attractor states like the looping intrusive thoughts in OCD or depression in real time, at the level of the thought itself.
That is an immense, almost philosophical interpretive leap.
How so?
Well, I will readily concede that reading quantum superpositions in microtubules might provide an astronomical bandwidth of data. We would be drowning in high-resolution biological data.
Which is a good thing.
Sure, but there is absolutely no evidence that semantic meaning, what you and I experience as a subjective thought or an intention, is perfectly and linearly encoded in the quantum states of 8 tryptophan molecules inside a single nerve cell.
But the fractal scale invariant nature of the brain's oscillations suggests that those quantum states dictate the macro states. The micro determines the macro.
They might dictate the exact microsecond timing of an ion channel opening, sure, but timing a cellular gate is not the same thing as encoding the concept of a sunset or the emotion of grief.
You don't think they correlate?
That is where I fundamentally challenge the printout metaphor. What if the macro-scale action potential isn't just the exhaust fume of a quantum engine?
What if that large-scale electrical spike is the fundamental unit of meaning for the brain's network?
Interesting.
The paper assumes that Layer 6, an external AI utilizing a transformer architecture, much like modern large language models, will magically decode these terahertz-level tubular vibrations into coherent cognitive thoughts.
With enough data, an AI can map anything.
I suggest that if you plug a deep learning model into the quantum optical fluctuations of billions of proteins, you are not going to read a thought. You are going to get an ocean of sub-computational noise. You are reading the quantum mechanics of the hardware, not the software of the mind.
I appreciate the distinction, but the classical electrical layer and the underlying quantum layer are not two separate, disconnected systems. They are intimately nested.
Nested how?
Research into something called the cation-pi interaction shows that classical chemical neurotransmitters, like acetylcholine, actually bind to brain receptors via the exact same aromatic ring structures that carry the quantum signal.
Okay.
The chemical transduction event converts extracellular chemical signals directly into intracellular quantum states. It is a continuous language. If an AI can decode the crude, blurry signals of action potentials today to let a paralyzed patient move a cursor on a screen, applying a transformer AI to a signal with orders of magnitude higher spatial and temporal resolution will absolutely yield semantic mappings.
You think the patterns will just emerge?
The patterns of thought are there. We just haven't had a lens capable of seeing them without blurring them into statistical averages.
I don't dispute that the resolution would be unprecedented. We would see the brain at a fidelity we've never imagined.
Exactly.
But to assert that correcting an attractor state at the excitotonic level will cleanly resolve a complex psychiatric condition like treatment-resistant OCD or schizophrenia without any unintended cognitive side effects, well, it demands a biophysical perfection that biology rarely affords.
It's theoretically possible.
We are talking about beaming quantum optical perturbations back into the human prefrontal cortex to alter thoughts. The potential for catastrophic interference with a person's native cognitive processes, their very sense of self, is non-trivial.
Which is exactly why the forward research agenda proposed by Enfield is so vital. He isn't suggesting we jump straight to human trials tomorrow.
I would hope not.
Priority 1 is strictly the in vitro synthesis of these yeast fibrils in a lab, verifying if we can reliably insert those tryptophan molecules. Priority 2 is measuring how long that quantum coherence actually survives using 2D electronic spectroscopy. We build the foundation biophysically on a lab bench before we ever touch a living neuron.
And I wholeheartedly support that research agenda. I think integrating the structural biology of prions with quantum sensing is a fascinating scientific frontier that will yield incredible discoveries.
It's groundbreaking.
It is, but we must remain grounded in how we evaluate the end goal. The proposal builds an incredibly precarious tower of assumptions, from wireless energy coupling distances surviving the pulsing of a heartbeat to perfectly cloaking radioactive isotopes from highly reactive immune cells, to extracting high-level semantic meaning from the subatomic vibrations of a protein.
It's a tall order.
It demands absolute perfection at every single layer in a physiological environment that is fundamentally messy.
Well, let's bring this to where I believe we find robust common ground. Because regardless of whether Enfield's specific 6-layer architecture works exactly as hypothesized down to the last nanodiamond, his critique of the status quo is absolutely unassailable.
I agree.
The traditional electrode paradigm is exhausted, and our non-invasive alternatives are woefully inadequate. Functional MRI or FNIRS, which measure blood flow through the skull, have a delay of 2 to 6 seconds. By the time you see the signal, the thought is long gone.
Way too slow.
And standard EEG has a spatial resolution measured in centimeters. It's like trying to listen to a specific conversation from outside a stadium.
On that, we are in complete agreement. We absolutely need interfaces that operate closer to the actual speed and scale of human cognition.
Right.
Relying on the metabolic shadow of blood flow or the blurred electrical potentials penetrating through the thick bone of the skull will never give us the high-fidelity, bidirectional neuroprosthetics we need to cure neurological disease. Moving away from rigid immune-triggering materials is an absolute biological necessity.
Precisely.
The material we've explored today forces the scientific community to ask profound questions. It forces us out of our comfortable material science silos where we just keep trying to make softer and softer plastics, and demands we look at the quantum nature of neurobiology and the true origin of cognitive computation.
It certainly does that. It deeply challenges the prevailing assumption that the brain is merely a classical wiring diagram made of meat. Whether the ultimate solution is this specific ambient amyloid scaffold or something else entirely, it proves that if we want to talk to the brain, we have to start speaking its actual molecular language.
And that leaves us exactly where we started, looking at the limits of our engineering paradigms. Are we going to keep treating the brain like a rigid machine, trying to fix it with the brute force of mechanical engineering, classical physics, and silicon needles?
Or find a better way?
Exactly. Are we going to recognize that the biological reality is infinitely more subtle? Perhaps the human brain is not a classical electrochemical engine waiting to be wired into. Perhaps it is a quantum optical device, just waiting for the right conversational partner?
Today, we're diving into a brain-computer interface concept that is just radically different. I mean, forget everything you know about silicon probes, metal electrodes, all of that. We're talking about a BCI that isn't just compatible with life, it's literally made from life itself. And this quote right here, this really sets the stage for everything. It completely reframes the whole problem, doesn't it? The goal isn't to build a better tool to poke the brain with. It's to create a partner for it, something the brain can have a real conversation with because it speaks the same language. So, why the big shakeup? Why do we even need such a radical new approach? Well, it all boils down to a fundamental flaw, a biological problem that honestly plagues every single BCI ever built, from the earliest clunky designs to the most high-tech stuff we have today. Okay, so here's the problem in a nutshell. Every BCI right now is made of stuff that's foreign to our bodies, silicon, metal, polymers, and our brain's immune system is brilliant at its job, which is to find and attack foreign objects. So these immune cells, they swarm the implant and they build this biological wall around it. It's called a glial scar. And you have to understand, this isn't a failure of the BCI, it's a success of our immune system. But the end result is always the same. The signal quality just plummets over time, making these things basically useless in the long run. And this right here is where the entire game changes. For decades, we've been stuck on the left side of this chart, right? Trying to make a foreign thing more acceptable, trying to trick our biology with fancy new materials. But the new idea, the premise on the right, it just flips the whole script. Why on earth would you try to trick biology when you could just build the interface from biology itself? So how do you even begin to build with biology? Well, you start by learning its native language. And it turns out the electrical spikes we've been measuring for a century, they're just the end of the story. They're the final output of a much, much deeper and faster computation that's happening at the quantum level. Okay, get this. Deep inside our neurons, we have these incredible structures called microtubules. You should think of them less like simple little bits of scaffolding and more like quantum fiber optics. They're packed with these special molecules that create these perfect pathways for energy to travel at absolutely mind-boggling speeds. This whole process hums along at terahertz frequencies before it ever slows down to become the electrical signals we can measure. So our neurons aren't just wires, they are, in a very real sense, tiny quantum computers. This whole magical process is called exciton transport. It's a really cool quantum trick for moving energy around with almost zero loss, where the energy just kind of hops between molecules. You know who mastered this billions of years ago? Plants. It's how photosynthesis works. And it turns out our brains have been using the exact same playbook all along. So this brings us to a really crucial point. If all that quantum stuff is the actual computation, then the electrical spike, the action potential that every single BCI today is designed to read, that's just the final printout. We're showing up late to the party and only reading the final answer, completely missing the incredibly fast and complex quantum calculation that produced it. All right, so how in the world do you build an interface that can speak this quantum language? The solution is as elegant as it is brilliant. You use the same biological building blocks that the brain already knows and uses. The secret sauce here, believe it or not, comes from yeast. It's a specific protein that, because it's from yeast, our brain's immune system just completely ignores it. No attack, no glioscar. This protein naturally assembles itself into these incredibly stable, almost crystal-like fibers. And here's the genius move. Engineers can actually place those same energy-conducting molecules from our neurons into this scaffold, creating a perfect quantum highway to connect directly with the brain's own network. So this is basically how it all stacks up. First, that biological scaffold just sits right on the surface of the brain. No needles, no penetration. And it links up with the neurons through quantum resonance. Simple. Second, you have tiny sensors embedded in the layers to actually detect all those quantum signals. And third, the whole thing is self-powered. It harvests tiny bits of energy from your body's own heat and movement to send all that data wirelessly. It's a complete, self-contained biological interface. Okay, so what actually happens when you have an interface that can finally understand the brain's native language? Well, the possibilities just explode. We're not just talking about moving a cursor on a screen anymore. We are talking about a totally new level of human-machine interaction. I mean, really think about this for a second. This is the big shift. Instead of just decoding the signal that says, move your hand, an interface like this could potentially access the actual content of your thoughts. It could tap into the prefrontal cortex and literally read your working memory. We're talking about a true thought-controlled interface for the very first time. The implications here are just staggering. First, you get true thought control, reading not just movement, but your actual intent. Second, cognitive augmentation becomes a real possibility, a two-way street where the interface could help enhance your memory or decision-making. And maybe most importantly, this could lead to transformative new therapies, where you could precisely correct the scrambled circuits that cause things like depression or PTSD, all in real time. So, here's the final idea I want to leave you with. For all of human history, our relationship with technology has been a monologue. We tell it what to do. But now we're standing on the edge of a true dialogue. A real conversation, not just with our gadgets, but with the deepest, most fundamental computational layers of our own minds. And what they're going to say to each other, well, that's a question that could define our entire future.